Hi there, and welcome to this channel where we try to answer the great questions of the universe. One such question that is currently very relevant is, what is nuclear energy? It's been in the news a lot lately, especially with the conflict in Ukraine and with 44% of the electricity generation in Europe coming from nuclear power. It's important that we all understand it better. In the simplest terms, nuclear energy is generated through the process of nuclear fission, which means the splitting of an atom. If we take a look at uranium, which is one of the most common elements used for nuclear power, each one of these little balls contains around 92 protons and 143 neutrons, making up an atomic mass of 235. Now, if we were to fire a neutron at this guy, it would probably go straight through because there's a whole lot of nothing in between those protons. But if that neutron happens to collide with one of the protons, things can get interesting. The neutron gets absorbed by the nucleus, and the resulting instability causes the uranium atom to split into two smaller atoms, which are here represented by these two smaller balls. The original uranium atom, also called the fissile or fertile nucleus, splits into two or more lighter nuclei or daughter nuclei, and the neutron that was fired at it. It's not absorbed in the process, but rather released. This released neutron can then go on to strike other uranium atoms, causing them to split and release their own neutron, and so on and so forth. This is called a chain reaction. And it's exactly this chain reaction that releases an extraordinary amount of energy. It takes just one single uranium atom splitting to trigger a massive amount of splitting and energy production. The energy is released in two ways. Firstly, the mass of the products is always slightly less than the mass of the reaction, and according to Einstein's famous equation, E equals mc squared, mass can be converted to energy. In the case of 1 kilogram of mass being converted, that would yield 9 by 10 to the 13th joules of energy. Secondly, the daughter nuclei are formed in an excited state, and they return to a stable state by emitting gamma radiation. Now, this energy would be useful to us if we could control it. So let me show you how that is done. The process of nuclear fission was first discovered in 1938. And since then, we have come up with various ways of harnessing its power. The most common type of nuclear power plant uses something called a pressurized water reactor. Let me show you how it works. We start with fuel rods made of uranium held in a metal tube. These tubes are then placed inside a big container full of water known as the reactor core. The entire reactor core is surrounded by a containment structure, which is really the whole point of nuclear power plants, to keep everything contained. The water in the reactor core does a couple of things. Firstly, it moderates the neutrons, meaning slows them down so that they're more likely to cause further splitting. And secondly, it acts as a coolant, taking away the heat produced by fission. The water in the reactor core is under high pressure, which prevents it from boiling. However, once the water has absorbed enough heat, it is pumped out of the reactor core and passed through a steam generator. Here, the hot water in the primary loop is separated from the water in the secondary loop by a solid barrier. Heat is transferred to the secondary loop, turning it into steam, which then drives a turbine connected to a generator, which produces electricity. After that, the steam is condensed back into water and returned to the beginning of the secondary loop. It is good to know that nuclear power plants are designed with multiple layers of safety features to prevent any meltdown, i.e., uncontrolled energy release. For example, even if the water stops circulating, there are passive systems that will kick in and allow the core to cool down. And even if the emergency core cooling system fails, which really is the last line of defense, the energy released by the core would be dispersed into the surroundings, leading to a meltdown. But even then, modern nuclear power plants are built with a robust containment structure that can withstand extreme temperatures and pressures. The only real danger is human error or malevolent attacks. Another type of nuclear fission reactor that you might have heard about is the breeder reactor. Unlike traditional reactors, breeder reactors produce more fuel than they consume. This is because when a fissile uranium atom splits, it doesn't necessarily split into stable daughter products. Sometimes it results in a fertile nucleus that can capture a free neutron and transform itself into a fissile nucleus. The process of converting fertile nuclei into fissile ones is called breeding. So in a breeder reactor, the rate of breeding is higher than the rate of consumption, leading to an increase in the number of fissile nuclei in the reactor. The most common type of breeder reactor is the fast neutron reactor, which uses liquid fuel instead of solid fuel rods. Fast neutrons don't moderate like slow neutrons do, and they can still cause fission in certain fertile nuclei. One example of such a nucleus is plutonium-238. So in a fast neutron reactor, some of the uranium-238 in the fuel can be converted into plutonium-239, which is another fissile nucleus. The key difference between a breeder reactor and a non-breeder reactor is the type of fuel they use. In a breeder reactor, the fuel is a mixture of uranium-235 and uranium-238, whereas in a non-breeder reactor, the fuel typically consists of only uranium-235. Now, nuclear power is often contrasted with thermal power, which comes from burning fossil fuels such as coal or gas. Both processes work by heating water to produce steam, which drives turbines. But nuclear power is much more efficient than fossil fuels because it heats the water directly. Whereas in thermal power, the heat from the burning fuel is transferred to the water indirectly. Also, nuclear power plants produce much less pollution. They do produce radioactive waste, which needs to be carefully managed for thousands of years. But compared to fossil fuels, they emit virtually no greenhouse gases. And if that wasn't enough, new nuclear reactors are very safe. Modern designs use something called a passive cooling system. This means that the reactor doesn't need an active water pump to cool down the fuel. Instead, it relies on natural processes such as convection, currents, and gravity. This makes it extremely unlikely that the reactor would overheat or melt down. Finally, nuclear power is incredibly powerful. Just one single nuclear power plant can generate enough electricity to power a city of 500,000 people. For example, the largest nuclear power plant in the world, Kashiwazaki Kariwa in Japan, has a capacity of 8. That means it can produce up to 8.2 billion watts of electricity at full capacity. By comparison, the average household uses around 1 kilowatt of power. Of course, nuclear power isn't all sunshine and rainbows. It has its fair share of problems. First of all, building a nuclear power plant is expensive. It costs billions of dollars and takes several years to complete. Secondly, the fuel is expensive and hard to get. Uranium mining is a dangerous and environmentally damaging process. And lastly, what do you do with the waste? Now, that's actually not such a simple question. You see, nuclear waste remains radioactive for thousands of years. It can't be dumped anywhere. It has to be carefully sealed and stored in deep underground repositories. Now, there are many places that claim to have found solutions to long-term nuclear waste storage. But so far, none of them have been accepted as safe and permanent. The difficulty of dealing with nuclear waste is one of the main reasons why countries like Germany and Belgium have decided to phase out nuclear power. On the other hand, countries like France, Sweden, and Finland are investing heavily in new nuclear technologies. They're betting that nuclear power will play a major role in the transition to renewable energy. So what do you think? Is nuclear power the future, or is it too risky? Let me know in the comments below. I hope you enjoyed this video. If you did, please subscribe and check out my other videos. Thanks for watching, and I'll see you next time.